Okay, I think it's time to start. So I have the great pleasure to introduce a great combo, which is Fabian Renn-Giles and Dave Rowland, who have been in the audio industry for, I think, probably, I wouldn't be wrong to say almost 15 years, right? Something like that. Yeah, so Fabian used to work in the Juice team, for those of you who don't know, and he's now an independent freelancer and consulting software engineer. I think running your own business as well, fielding the SP, so he's doing a couple of things. And Dave Rowland is the director of software at Audio Squadron, who owns Traction, which I'm sure you're familiar with. And today, they'll be showing us how to live peacefully in a lock-free world, I think. Yeah. Please join me in giving them a warm welcome.
Yeah, I think we don't need to add anything to that introduction, do we? Cheers, Vlad. Okay, so can I get a quick show of hands first? Who does real-time programming? Good number of people, okay. So, well, we can all leave and we don't need to tell you anything. Okay, so quick bit of prior art. Has anyone seen Timur Dumla's talk, C++ in the audio industry from CPPCon? Good number of people. And has anyone read Ross Benzina's Time Waits for Nothing article? Okay, if you haven't, well worth a watch and a read of those two things. They're great primers for some of the stuff we're going to talk about today and give some more background. Also, if anyone has any questions during any point in the talk, if you don't understand something on a slide or whatever, raise your hand and we'll try and answer questions as we go, just so kind of anything is answered. So let's dig into, first of all, what does real-time mean? There was a paper in '94 that kind of went into real-time systems as a whole, but gave this definition, which was, a system is said to be real-time if the total correctness of an operation depends not only upon its logical correctness, but also upon the time in which it is performed. So the key thing here is you have some input, you're doing some kind of processing to generate an output, but not only does that output need to be logically correct, it has to be the right answer, but it also has to be formed within a specific deadline. So deadlines is really what we're talking about today. And if we go further on from that, we can see that real-time systems, as well as their deadlines, are classified by the consequence of missing a deadline. And we can roughly split this up into three categories. So we have hard, where missing a deadline is a total system failure, and we see some examples of that on the next slide. We have firm, where infrequent deadline misses are tolerable, but may degrade the system's quality of service. The usefulness of a result is 0 after its deadline. So this is our classic audio problem, really. If you think about some examples, such as playing an audio file from your computer, it might be okay if you drop the occasional packet, you can still continue. In a hard real-time system, that wouldn't be the case. Of course, if you're recording a 100-piece orchestra, or playing at a music gig with tens of thousands of fans, you don't want to hear any clicks and pops. So your constraints will vary a bit depending on what you're doing. Also, we have soft real-time, which is where the usefulness of a result degrades after its deadline, thereby degrading the system's quality of service. So we can see our soft real-time systems on the left-hand side here, which are things like production lines, where you might have other parts of the system depending on one, and if one slows down, it just kind of possibly grinds everything else to a halt. But it's still useful to have the output of those parts of the system. On the right-hand side here, we can see hard real-time systems, and these tend to be mission-critical systems, like car engine control systems, anti-lock brakes, medical equipment and monitoring systems. If you think about a pacemaker or a machine that's going to deliver medication to someone, you can't go, oh, I'll just do that tomorrow if the deadline's missed. People die when that happens. So we're mainly going to be talking about this firm real-time area in the middle, which encompasses audio, things like video game visuals. You can imagine if you're running at 60 frames per second and you drop a frame or two or have a stuck frame, most people aren't going to notice that. High frequency or low latency trading sometimes falls into this gap as well, because you sort of have different trade-offs depending on what type of system you're running. So there's different types of limiting factors when we're talking about real-time systems, and there's kind of three main categories. The first one is latency, which is your deadline. How long does it take to generate your output once you have some input? Then we have bandwidth, which is how much processing can you do without missing your deadline. So in a DAW example, you might think of bandwidth as how many plugins and how many effects can I add to this track before I start getting buffer underruns. And jitter is essentially the difference between your latency for each block. And in real-time systems, you kind of need to keep that jitter within your deadline window. So let's just have a quick look at what could go wrong. So we mentioned games and visuals where you get dropped or stuck frames. In audio, you might get clicks and glitches in the output, and they're essentially immediately obvious. Once you've dropped a packet, you can't really make up for that. High-frequency trading is where things start to get kind of serious. There was an example Nimrod Sapir gave in his talk at Core CPP, where a trading company, I think what they ended up doing was shipping debug code in their production build, and they lost $10 million a minute, and they lost $10 million a minute, 45 minutes. So you don't want to make these mistakes. And also, we mentioned in life support and monitoring systems, people can die. So this is important to get right. So how do we think about real time? Well, in software, if you have an API that you're calling or you're developing an API and you state that it is real time, you are making a contract with whoever's consuming that API that you will complete in a deterministic amount of time. This is kind of dependent on resource contention, but what we're talking about is there are no unbounded calls, and we'll dig into that in a little bit more. Quick note, if anyone's following like the C++ standard, this isn't the same as a contract check-in statement, which were actually removed from C++ 20 recently, but they'll probably be back in 23. And also, because of this, there's no way to state this currently programmatically in C++, and we'll maybe dig into that a little bit at the end. So that's kind of the background to real-time and how different industries use it. Now we're going to look at how kind of computers work in real-time systems. So essentially, modern operating systems have multiple threads, and the threads are scheduled by the OS. We're going to ignore process scope threads here because they're kind of a bit complex, and if you start a std thread or anything like that, they're governed by the OS most of the time. And how frequently they get run for and how long depends on the thread priority and the scheduling algorithm of the thread scheduler. So threads can essentially be in kind of three states. They can either be running, so they're currently processing on a core. They can be sleeping, so they're not being run and aren't able to be run. Or they can be in a ready state, which means they're not currently being run, but they are able to be run. And these states change depending on things like system calls, which could be an IO operation, or you can do them explicitly by using library calls like thread sleep for, condition variable, notify one, all, and wait. So these things explicitly signal to the thread scheduler what to do with that thread. And then once you've kind of notified the state, the thread scheduler needs to decide which threads that are in its ready state to run. And this will be based on priority, the last time they're run, and a whole other bunch of heuristics that it has. And when a thread goes from a ready to a running state, this often involves a context switch. And we'll look into what context switch is in a sec as well. So in a very simple way, this is kind of what a thread schedule looks like. So you have a 2-core CPU. Each of the different colors is a different thread, and you kind of get put onto a core, do a bit of processing, moved off a core, and you can jump around different cores. And this is kind of for your standard threads. One thing to note here is that we have some empty space, and that's because on general purpose operating systems, you're contending with other processes. You might be run more frequently if you're the foreground process, but you have to be aware that there might be other things jumping in and out. However, in real-time programming, we have a slightly different scenario where we have something called a real-time thread. And a real-time thread essentially has different privileges. A real-time thread can give you an uninterrupted period of time to run, but if you miss the deadline that you're supposed to complete by, then you may be put to sleep. And if you're put to sleep, there's a good chance that you're going to miss your deadline and cause buffer underruns and all the problems we saw before. But also, you may be declassified as a real-time thread. And if this happens, then you lose your real-time privileges, and you'll end up just being scheduled as a normal thread in subsequent callbacks. And once you're in that situation, it's very hard to meet your deadlines. So the key takeaway here is that you don't want to miss your deadlines. And I'm going to reiterate that because that is the most important thing. You need to do everything possible to not miss your deadlines. And if we go back to our graph, we can kind of see that this red block here is now how a real-time thread behaves in comparison to other threads. So now that we've kind of seen how thread scheduling and kind of contention in the system works, what are some of the problems that can cause us to miss our deadlines? If we take a look at this table, on the right-hand side, we can see that we have essentially everything on the left available to us when we're doing non-real-time, including things like system calls, exceptions. But in a real-time context, a lot of these are not available to us. So we have to do some CPU work. We're generating some output for some given input. We may have to do context switches. There's situations, particularly kind of on lower level systems, bespoke embedded systems, where you can dedicate a specific core to run your real-time thread. But especially on desktop operating systems, your thread is going to have to be switched in and out, which will involve a context switch. And you're probably going to need to access some memory at some point. The key thing here is to avoid paged memory. And I'll go into that in a little bit more detail as well. System calls we need to avoid, because system calls are blocking operations. They essentially have to synchronize with the rest of the OS, so there's no way to know exactly how long that's going to take, because you're now contending with the rest of the operating system. Similarly, allocations, where you're asking for memory, they're going to take an unbounded amount of time, because another lower priority thread might be asking for memory at the same time. Deallocations are essentially the same problem as allocations, but I put them in as a separate note because they can sneak in destructors. And if you have lots of RAI objects, you kind of need to be aware of where deallocations are going to come from. Exceptions we can't really use because these involve a memory allocation, and priority inversion is also a problem. So if we dig into some of these in a bit more detail, what is a context switch? This kind of comes up quite a lot, and why is it a problem? What happens when your thread goes from a ready state to a running state is it will be stored, your thread state will be stored in some memory somewhere. It might actually be part of the chip if you have like hyperthreading, but you're going to have to reload the state of that thread into the processor in order for you to continue where you left off. And this includes things like registers. If you're currently doing calculations, they need to be loaded back into registers for that to happen. And also machine state flags, things like whether denormal prevention is turned on. These need to be reloaded because they can vary between threads. You have things like the stack pointer and the program counter. And also, if your process is changing as you're switching threads, your address space will change. So these are all things that need to happen pretty much constantly in a modern operating system. The other thing is that when this happens, you might make a switch from user mode to kernel mode if you're waiting for an I/O resource. And the other thing is that when your thread gets moved on and off the core, this can involve invalidating caches. So things have to be pulled back from either higher level cache or even memory for them to be ready to be used. So what is the difference in memory accesses? Well, first of all, you kind of have registers where operations are performed. Then you have different levels of caches. Then you have RAM, and then you have disk. And what you really want to avoid here, or what you want to try and achieve, is as hot memory as possible. So that means closer to the CPU. What we really want to avoid is disk accesses, because disk accesses are highly contended, and disk is incredibly slow compared to everything else. And this can kind of happen in perhaps unforeseen ways. Say you're running some audio samples and you've loaded half a gig, couple of gigs of piano samples, but some of them aren't used very often. And then you've got a synthesizer that wants to play those back. The note that you're playing constantly may be kept nice and hot in memory, but then if your process gets switched out, something else comes on, it wants to load a load of memory, that's going to get pulled into memory, which might mean that your samples that you wanted to read from actually get paged to disk. Now when your process gets called back, you think, well, I've just got some memory here, I'm going to read my audio sample, but what actually happens is the operating system has to go to the disk, seek to the right position, load that back into memory, and then down through the cache chain for you to read it. So this can be a very costly operation. There are some techniques that we can do to try and minimize or avoid this. A common technique is to have another thread that kind of constantly goes through and pokes your large file, or at least the bits that you're going to be reading, which indicates to the OS, hey, don't page this out. And the other technique is to use mlock, munlock on POSIX, or virtual lock, virtual unlock on Windows, which is an indication to the OS to never page that to disk. You have to kind of be careful with these, though, because if you just allocate tons of memory and then stop the OS from paging anything, then your system will grind to a halt, and you're kind of back to square one. Just to give an example of how cache and memory relate to each other. Has anyone seen Mike Acton's talk from CPPCon in 2015? Is it 2015? Yeah, a lot of people. So he's the first person I saw do this, but I've seen Scott Miles do it as well. So just to get a rough relationship between the different levels of cache, if we look at L1 first, this is kind of how long it takes, so nice and quick. L2 is a bit longer. If you're reading for RAM, which is still memory, remember, that's kind of proportionally how long as it takes. This is to scale, so we might just have to wait a while. I was going to put how long a disk read takes on here, but it can be up in the order of 10,000 times a RAM access, so that would take a couple of days for the animation to finish. So that's the situation you really want to avoid. So once we've kind of dealt with the memory problems, we can look at some of the other things. So priority inversion is a classic example. In a lot of our slides, you'll see at the left-hand side a red bar and a green bar. That is distinguishing between the methods or functions that are being called in a real-time context and those that are non-real-time. So in this kind of very trivialized example, we have a shared resource, this std vector, and we're going to guard access to it with a std mutex. We have a high priority thread that's going to take a lock, so it's going to prevent any other threads from modifying this. And essentially, it just wants to do some processing. It's just multiplying by 0.1 here for some silly reason. Then you have the non-real-time thread, which is running at a lower priority, which wants to resize that for another unknown reason. But what happens if the low priority thread gets here first? So it takes the lock and then starts resizing. Now the high priority thread wants to come in and use this resource, but it's going to have to wait for the low priority thread to finish its operation. Now this resize, this memory allocation, could then also be waiting on something else that's doing some memory allocation. So now your high priority thread is essentially completely blocked. And we call this priority inversion because its priority has been inverted to essentially the priority of the lower, the non-real-time thread. Now, this might seem like a trivial example, but these things can sneak in hidden places. If you've ever used a std shared pointer, you might think, okay, I want to atomically swap shared pointers. I want to load from one thread to another. Maybe I'm passing some big resource around. But if we dig into atomic store, and atomic load is essentially the same here in libcpp, we can see that there's this mutex at the top here. So the first thing it does is get a lock to guard access to swapping this pointer, and then takes it. So if you have a lower priority thread that's doing one of these pairs of operations, takes the lock, and then just happens to be descheduled whilst it's taken that lock, so it's gone back to sleep, then the high priority thread, or the real-time thread, is going to come in, and then it's going to wait to gain access to this mutex. And this is another example of priority inversion. I have had discussions with people before whether priority inheritance helps here, which is the idea that a high priority thread will come in, wake up a lower priority thread if it's contending for a resource, wait for that operation to complete, so then it continue on its way. But from what I can find out, priority inheritance is essentially disabled on real-time threads. So you can't really rely on it to help you out here. So you might be thinking, atomic std shared pointer. Well, we've got actual std atomic shared pointer coming in C++20, but it's not going to be lock-free. So Timur wrote this question on Twitter earlier in the year. He said, is this going to be a lock-free implementation? Stefan came up and said, I don't really know if it's possible. Then JF came in and he said, I also don't think it's possible. And then it's essentially a blame passing game of, well, someone's going to have to implement it. But essentially, it's a difficult problem, and we've kind of discussed this at length. And the problem is that you have a shared pointer as a pointer to a control block. And because those bits of data live at different addresses, there's no way to atomically modify them. We're kind of researching some other techniques with Timur and other people for how you might get a slightly more constrained lock-free shared pointer. But don't rely on something just because it says std atomic, basically. So what other things can cause us to miss our deadlines? Well, copies can. Imagine you've avoided all data races in your application, and then on your real-time thread, you call this method update data. There's going to be a problem here, because if new data has a different size, then this could reallocate and cause a problem. However, that kind of thing seems trivial, but it can sneak in hidden places. So imagine this scenario where you have legacy code. So you might have something like a legacy object, which just has copy constructor and assignment operators, and then you might create a kind of parent object, which contains maybe a vector and a legacy object, and then in your program, you write something like this. Does anyone know what the problem here is? Any show of hands? And Lucas down the front? Do you want to tell?
Yeah, although we say it's smooth, basically the idea behind the operator is only going to move if your objects are movable, but if they are not, it's going to use the copy.
Exactly. So because this is a legacy object, it doesn't have R-value assignment and constructors. So it's going to fall back to use this copy operator. So even though the std vector does have R-value semantics, it will do the correct thing. Legacy object is going to involve a copy. And if internally the copy is something like a std vector, then it's actually going to copy that std vector, and you might end up with the problem that we saw on the previous side. So yeah, we end up calling this copy constructor. So be aware of hidden costs, because they can be deeply nested.
So we're all still in the introduction, so bear with us until we get to the main part of the talk. But before we get there, let's just introduce some vocabulary so we're all on the same page. There are sort of three categories of nastiness when it comes to non-real-time code. And the nastiest one is when your operation blocks. And that means that your operation is doing something like taking a lock or doing a system call. And that's really bad, because when you lock or take a system call, it means there's going to be a context switch. That means some other process might jump in. That means by the time you go back to your application, your caches are not going to be hot anymore. Things will have swapped out. You might be on a different core even. So that's the one to avoid, if anything. Then slightly better is non-wait free. That means that that just means that your execution time is somehow unbounded. That means there's some kind of loop in your code, and you can't reason about exactly when that loop will exit. And we'll see some examples of that, like typically are spin locks or something like that. So they'll keep the cache hot and everything, but you can't reason about how long that will take. So you might miss your deadline. And the best thing is, of course, wait-free is no unbounded loops. You can reason exactly how long your code will take in a worst-case scenario, and then you know if you're going to hit your deadline or not.
So if we summarize kind of everything that we talked about there, it's actually quite simple. The rule is don't block. And this can be kind of split up into two things, which is don't make system calls and don't wait to acquire a lock of any kind. So if you remember those things, you're fine, basically. And also be aware of where these things can sneak in hidden situations. Okay, so now we're kind of going to go on to the real meat of the presentation and tell you some various scenarios and then typical techniques to win in real time. And the general idea here is that we're going to kind of ask ourselves a series of questions, and at each point we have an idiomatic solution. And what we want to do is kind of start at the top here, where life is nice and easy, we're in the clouds, everything's kind of fine and dandy, and avoid getting stuck too far down into real-time hell. And the main point of this is that real-time programming is essentially about trade-offs. And the trade-offs that you make depend on your situation and your requirements for the system. So this is what we're going to dig through next.
And as some of the design patterns we're going to show, especially down in when you're getting closer to hell, the design patterns get really hard to write and hard to write correctly. So as part of this talk, I released this library called Farbot, and it's basically a collection of real-time design patterns that I've used in production code over the years, and always shoved into this one corner of my computer and said, oh, it would be nice to release that one day. We're not going to talk about atomic memory ordering at this talk. We'll briefly mention it. The library does use memory order and all the fancy tricks there. And although this was used in production code and they're unit tested and everything, the problem is that when I wrote this library, I moved everything to a new library, rewrote everything, gave them everything nice names. You know, some of it was programmed when C++98 was still around. You know, modernized the code. And that just means there's probably bugs in there, because if you change any real-time code, the likelihood of introducing a bug is quite high. So it's still early alpha development, and the main goal is for everybody to contribute their real-time design patterns and add them to the library, and maybe we'll have something nice at the end of the day.
Okay, so the first question we need to ask is, are we sharing or passing objects between threads? So at this point, it's essentially saying, are you creating a copy that you are completely removing and then passing on to another thread for execution, or do you have some kind of shared data? If you're passing, then the solution is to use FIFOs, but internally FIFOs are comprised of a bunch of other things we're about to discuss, so we'll loop back around to those towards the end. However, if the situation is that you're sharing some data, then we need to move on to the next question. And before we even get into kind of the real-time problems, we should stop a minute and say, are we actually interacting with a real-time thread? Because if you're not, then the solution is really to just use locks. And of course, there's std mutex we can reach for here. If you're sure that you aren't interacting with the real-time thread, it's a lot easier to build your program just using locks. Then profile it, check for performance bottlenecks, and act accordingly, perhaps introducing some lock-free stuff there, but use locks if you can. However, if you have answered yes to this question, then we need to go into another example. So the question here is, are we sharing suitably small data? That's a little bit cryptic, but we'll tighten up that definition next. So here's a classic example where you have some kind of variable that's shared between a real-time and a non-real-time thread. This gain in this instance. So on our real-time thread, we're kind of getting some sensor data, we're doing some processing to it, and then using this shared gain variable. In our non-real-time thread, we're setting the gain, so this could be from some kind of user input. Is this okay? How about on a single core machine? Show of hands, who thinks this is fine? Couple? Okay. It's not, because sharing data between threads where one of them is a write is a data race. And a data race is undefined behavior. And what can happen here is quite subtle. So one thing that could happen is that because the optimizer is going to assume that you haven't written a data race, it can assume that this gain value isn't going to change during the duration of this process data function. So what it can do is pull that gain out and actually just store it in a register. So in this instance, your gain isn't going to be updated when set sensor gain is called because it's stored in a register. And you might think, oh, that's not too bad. I kind of just reduced the resolution of my gain change, so now it's happening every block. But your code might not look like this after the optimizer is done with it. You might have something like a real-time thread entry that references some other variable that's just going to loop continuously and then call your processor data method after it's got some data. Now, your processor data method here could be quite small, which means it might be inlined. So now your code looks like this. And if the same reasoning is applied to the operation from before, the gain is hoisted out into a register, it can end up looking like this. So we've essentially just cached gain for the entire duration of our real-time thread. Now our set sensor gain essentially has no effect because there's no way that it can modify what's in this register. So because we've written a data race, we've invoked undefined behavior, and literally anything can happen, including exploding rockets in this case. So this is a situation we want to avoid.
This is another really nice example of undefined behavior and how the optimizer can do certain things that you don't expect. So here we have, I mean, this is toy code, don't take this code too literally, but here we have something, somebody wants to disprove Fermat's last theorem, right? So what they do is they basically run this loop and check if any of these numbers for any n, and x, y, z are just random numbers, for any n, is Fermat's last theorem wrong, right? Like this should never be equal for n greater 3 or greater than 3. So they just loop around and check for any n, maybe one of them is wrong, and if I found a wrong one, then I've disproven Fermat's last theorem, right? Great. And the way the user is doing this, it's starting a thread to do this calculation, then after 2,000 seconds it says, well, if I haven't disproven it in 2,000 seconds, well, it's probably right, right? So then just return true. So that's the idea here. What do you think will happen, or what can happen? I mean, this happens on GCC trunk right now, so if you build the latest and greatest GCC, this will happen. But what do you think will happen in this code? Anybody care to stab a guess?
Loop will disappear.
Yes, exactly. The loop will disappear. Right. Very, very good. And well, let's go this in several steps. Okay. So first of all, we have this loop condition. We're reading thread running all the time, and just as before, thread running is shared between two threads. It's shared between this test theorem thread, where we change it to false, and reading it from this thread. And that's a data race. It's undefined behavior. And so if it's undefined behavior, the compiler may assume that thread running never changes, right? Because it looks at thread running. This thread is not changing the value, so it can assume it will never change. That's why a data race is undefined behavior. And some people find this very, very strange. But just think about if the compiler weren't able to do that. If the compiler weren't able to hoist that out and cache that value, it means here would be a memory read every single cycle. I mean, that would be a huge waste. Like, we want the compiler to do this optimization. And I hope every single step I'm going to go through now, I hope you agree that we really, really want the compiler to do these optimizations. So in this case, we really want the optimizer to sort of cache this value and not constantly read it from memory. So what is it going to do? Well, assumes you didn't write a data race, so it's just going to replace thread running with true. So now we have while true. Okay, so that's what the optimizer is going to do in the first step. Now, another optimization kicks in. There's a whole, in Clang and in GCC, there's a whole host of loop optimizations. And before it does that, it's going to bring the loop into a canonical form. And that canonical form, what it tries to figure out is what the condition for that loop actually is, because loops can be very complex. So it's going to look at this loop and going to say, what is the actual condition of this loop? And it's going to say, oh, this is the real loop condition. So let me just remove that loop condition up there, right? And transform it to this, right? So now this is the loop condition, and if the loop ends, it's going to return false, right? Okay, so this is a good optimization. We haven't changed the code here, really, right? This is just transforming the way the loop looks. Now another optimization kicks in. It's going to say, wait, hey, that looks like dead code to me, right? It's never going to reach that. Let's just eliminate that right there. And then another optimization kicks in, the last optimization, which is also an optimization that's very, very useful in templated code. And it's going to look at this function. It's going to say, well, a function that never returns. You cannot in C++ write a function that never returns. That's also undefined behavior. Every function in C++ must return, or you write no return attribute. If you write no return attribute, this would be fine. But here, the compiler may assume that this function will definitely return. It can see that the only way the function can return is by returning false. And then it sees, well, this function doesn't have any side effects, right? We're not changing any memory. This is just a simple assembly instruction, this POW. We're not calling any system calls. There's no side effects of this call whatsoever. So of course what it's going to do is the only way to exit this function is by returning false. It doesn't have any side effects. So let's just replace the whole thing with false. And all of those, I hope you agree, all of those optimizations are good optimizations. We want the compiler to do these optimizations. But by applying all of them, some really unexpected things can happen. And this is something which is very, very difficult to debug if you have a large code base. Because you end up, let's say you put a breakpoint here, and you run your code in 03, optimized for release, and you suddenly jump into this place, and you're like, how did the code get there? This condition is never, ever true. I know this, right? I know Fermat's last theorem is correct. But still, the compiler somehow ends up in there. And why? It's because you've written a data race, right? So data races can be very, very tricky to debug and can lead to all sorts of effects that you just don't expect from your program. So don't write data races.
Big point there. OK, so if we return to our gain and sensor data example, back to the flowchart, we say, are we sharing suitably small data? And if the answer is yes, then we might be able to use a stood atomic. So in this example, we've replaced our plain float with a stood atomic float here, which fixes the problem for us here. And it kind of does it in two ways. First of all, it ensures that loads and stores are synchronized. So when we load and store to this variable, we're going to get the value that we expect. But also, it stops the optimizer from doing all of those tricks we saw before, because it knows now that it can't reorder instructions in the same way that it did before, or cache variables. So we've kind of fixed the two problems here. However, if we're using stood atomic, we need to check this assertion. So we need to check stood atomic type is always lock-free. And we need to do this to ensure that manipulating that data type is lock-free in hardware. If this returns false, then what will happen, as long as the object is trivially copyable, it will end up creating a kind of wrapper around your accesses to your object using locks, similar to the stood shared pointer we saw before, which is unbounded operation, so we can run into priority inversion problems. So we need to make sure that it's lock-free. So a short summary of stood atomic: it ensures tear-free synchronized manipulation of shared data. However, I just said it may use traditional locks if the data can't be manipulated atomically in hardware. The other key thing about stood atomic, remember we talked about trade-offs, is that you can only perform a subset of operations on stood atomic. So you can load, store from it, you can do atomic addition, subtraction, and you can do exchange, compare exchange, and we'll see some examples of that later. Notice there's no multiplication or anything in here, so you kind of have to think about your objects in a slightly different way. We're going to briefly mention memory order. It's quite subtle and complicated, so I've left Herb Sutter's, a link to Herb Sutter's Atomic Weapons talk at the bottom here. If you want to understand more about the C++ memory model and memory ordering, watch this. It goes into a real good amount of detail. But in summary, if you have a small independent piece of data on which no other data depends, you might be able to use a relaxed atomic to gain a small performance improvement. So you can use relaxed atomic if you don't care about the effects of that data. So something like a gain variable or a level meter that you kind of don't really care, you just want to know roughly what the value is. However, most of the time with atomics, you want your code to be executed as you've written it. And in that situation, you want to use the default, which is sequentially consistent. So that's the general recommendation, is to use sequential consistency. If you really don't care, perhaps use memory order relaxed. There is a middle ground called acquire-release operations. They can be useful in terms of things like FIFOs, where you only need to guard reorders of memory operations in one direction. but just stick with sequentially consistent, really, and watch Herb Sutter's talk. So in summary, we have a scenario here where we have multiple threads mutating a piece of shared data. The data is small, so this std atomic is always lock-free, evaluates to false, true here, but we can only do certain operations on the data. And I already mentioned some of the examples: game values, level meters, automation values, parameters, small individually settable pieces of data. So now if we go back to our flowchart, we can kind of tidy this definition up and say, are we sharing is always lock-free data? And if we are, we can use std atomic. However, in more complex situations, we might end up in this no branch here. So we need to move on to the next question. And this is failure to acquire the shared resource okay? And if it is, then we might be able to use a try-lock operation. So here we have another classic example where we have some kind of real-time audio callback that is doing something with some larger data, wavetable, several hundred floats, something like that. So we store our wavetable in a unique pointer so we don't leak it, and then we guard access to it with some kind of mutex object. In our non-real-time thread, which might be the user loading a new file or something like that, we create a new wavetable, then we guard access to the lock, to the resource using the mutex, and then simply swap the old and the new. So we know nothing else is going to be writing to this wavetable at this time. Then once this goes out of scope, we can safely delete the old one, which is essentially going to make the new one available to the real-time thread. In the real-time thread, we can do this operation called a try-lock. So we can't take a strong lock because we'd never want to wait on the non-real-time thread, but we can do this quick operation called a try-lock. So here we use std unique lock with this std try to lock argument, and then we can check if we've actually owned the lock. If that succeeds, then we can do something with our wavetable. However, if we failed to use the lock, it means that the non-real-time thread currently has it locked, so we don't have access to it. In this situation, we need to be able to do something sensible here. And what this means, if this fails, it means that this is currently loading a new wavetable, so we're going to lose access to that wavetable anyway. We might be able to just say, OK, we'll just pull our kind of deadline or our use of that resource forwards and just emit silence for a while. You probably don't want to just emit silence from your audio stream because you'll get a glitch, but if you perhaps remember the last sample or last few samples, you can kind of nicely fade out to avoid clicks. So in this scenario, that's our kind of trade-off that we're making. But we need to really look at what this mutex is. We've just written kind of cryptically mutex, it's not std mutex, because there are some other implications. What happens here when this std unique lock goes out of scope? This is a little bit weird because it's a C++17 if with initializer, which kind of puts braces around the whole operation. So that's actually where it goes out of scope. If we look at std mutex try-lock, it's always wait-free. That's great, that's a good tick. However, if we look at the documentation, we can see one problem, which is it can fail spuriously. And this can happen in some weird situations. It's probably quite unlikely, but it can happen, similar to how condition variables have spurious wake-ups. And this probably isn't OK. If you're using a wavetable or reading a file or something, and occasionally you might not be able to get access to that resource because of a spurious wake-up, then you will drop a packet and get a glitch. But more importantly, std mutex unlock can block. And it can block in situations where another thread might be holding the lock currently, and it needs to, or waiting on the lock, sorry, and then when you go out of scope, you need to make a system call to notify the thread that's waiting. So this is a blocking operation because it's a system call, which means we shouldn't use it. We can fix this problem, though. Rather than using a std mutex, we can use a spin lock. And if we simply replace all instances of our mutex with spin lock here, this operation works now because taking the lock or taking our try lock is wait-free and also is wait-free to unlock. And if we dig into what a spin lock is, this is a really basic spin lock, but it kind of helps identify the point. We have a std atomic flag. We have two operations available to our real-time context. We can unlock it, which simply clears the flag, or we can do this try-lock operation, which is going to try and set the flag from effectively 0 to 1 and return the old value, which is why we have to invert it. So this is essentially going to say, can I lock it? And if not, OK, I'm going to fail. In our non-real-time thread, we can do a hard lock operation, which is going to continuously try and set the flag and spin if it can't. So that's going to be a hard blocking operation. You can optimize this slightly. You can add CPU pause instructions and back off to avoid kind of continuously spinning. And this also helps the CPU schedule these operations appropriately. And you can also use acquire release semantics on the test and set and test and clear operations. But the key thing is that we have no sleeps and no yields. There's no system calls in here. We can only use try lock and unlock on the real-time thread and lock from non-real-time threads. So in summary here, we have a scenario where the data is big, stood atomic, is lock-free, is false. Failure to acquire the shared resource is OK. We saw this as a situation that we can deal with not getting the resource. But we have a couple of trade-offs. One is that the non-real-time thread waits on the real-time thread for access to the resource. If your real-time thread is continuously running, essentially never pausing, and your non-real-time thread wants to kind of jump in to do this atomic swap, it might happen that the scheduler kind of always misses its window to do this, so you can end up blocking for a long time. So be aware of that. And also, we said several times we have to fail gracefully. So some examples of this are where we're passing large data from a non-real-time to a real-time thread, such as audio samples, wavetables, filter coefficients, that kind of thing. So we've seen the situation where we can use a try-lock, but if failure to acquire the resource isn't OK, then we end up in this no branch.
Should we?
I think we should stop here. We've stopped a little bit early, but the next example will take longer than 5 minutes. So if you want to take an early break and then come back after the break. Or questions.
Up until here.
Any questions? No? OK, it's quite difficult to see, so.
Right. Oh, there's a question.
There's one in the middle.
In the middle.
Do you have a mic, Vlad?
Yeah. Mic is coming.
Hi. From the example below, before, when we talked about atomics,
right.
Atomics also have disadvantages when it comes to optimizations, right?
Yes, I mean that's how you avoid a data race. So I mean, the exact definition is a data race is if you share data between two threads, and one of the threads is writing, and then the sentence goes further, and there is no synchronization primitives, and synchronization primitives are atomics, locks, so mutexes, and system calls. Or well, it says I/O operations, which in practice is almost always system calls. So if any of those three things happen, then you've avoided the data race, right? And so that's what the atomics is doing. It's avoiding that data race. So that means the optimizer now knows it can't do any of those optimizations. If that was your question?
Yeah.
Yep. Okay. Yeah. Thank you. Exactly.
It's useful to perhaps think about your problems in a different way, because yes, you will remove all of those perhaps nice optimizations if you use atomics. So maybe think about, do I actually need to use an atomic here, or can I just, on-thread construction pass some data? It really depends whether you need to kind of update it live. There's one down the front here, Vlad.
It's a very quick one.
Okay.
Are the slides available for us later?
Yes, we'll put this version on. Is it on the Farbot?
Yeah, there's a shorter version. If you took a photo of the Farbot link at the beginning, I don't know if you did. In the README right at the top, there's a link to a shorter version of these slides. We'll put the longer versions up as well.
Yeah.
And there was a question over there. Oh, and there.
One here.
So just quickly, how do you determine if a system call is buried, several layers down from one of these kind of high-level things that are? Because I found like CPP reference is kind of a bit light on real-time details.
We'll discuss that in detail in the second
Yeah.
in the second part. It's probably not worth digging into now. Yeah.
Thanks.
Did I see one more up here?
Okay, this is going to take a while.
Come on, Vlad, quicker.
Can you achieve any kind of performance if you would avoid loading the atomic like every sample, as an example, instead of just taking a local variable at the end of the at the entry in the real-time thread?
Yeah, absolutely. I mean, you would have to try to mimic the optimizations that the compiler does with atomics, because with atomics, you're explicitly telling the compiler to not cache that variable. So you would probably want to re-add that cache yourself manually by taking a copy of by loading the atomic and putting the value of what you loaded into a local variable, and then use that. That's typically what you would do, exactly, yeah.
I have a question, so I'd like to maybe use my
Another
position.
one way up there, but.
Okay, well, after me then. So in your experience, do you have any sort of like types that you know are definitely suitably, what was the definition? I can't remember. Basically, you showed us that you can use the static assert way to check if it's always log-free.
Right.
Like, for example, on most platforms, like, do you know if a float is one, right? Like, sometimes testing that can take a while.
So you really need to use the assert, because especially if you're doing cross-platform stuff, it will change. In my experience, typically on Mac, Windows, Linux desktop operating systems, you can fit 2 floats into an atomic if they're in a struct, or if you use the Haswell flag and you're using Clang, you can fit 4. But that doesn't seem to be very portable. So in general, 2 floats is kind of the maximum.
I think almost every platform has integer atomic. So bool, definitely. So even the standard says that if you're using atomic flag and it's a bool, that's definitely lock-free. I think integers are always in practice lock-free. And then floats, it also depends. Even a single float, if, for example, you're an ARM and you don't have an FPU, then I don't think floats are lock-free. But I'm not sure. Maybe someone could correct me. I don't know. Yeah.
Definitely use the static assert. Okay. And one quick question.
One quick question. I think we're over time already.
Oh, is that Jerome up there?
Yeah.
Is this one working now? Nice. So for spin lock, is that included in the standard library, or is that something like that simple class you just made yourself?
That one's in Farbot, isn't it?
It's actually not in Farbot, but I should put it in Farbot. I mean, yeah.
Cool.
It's not in the STL.
That's you'll see that plastered all over the internet, that spin lock. It's just the most basic way you can write it using atomic flag. Right. But yeah, we'll add one somewhere.
Right, yeah.
Nice.
And one really quick, Jerome?
Yeah, just coming back to your very first example with the gain, remember? The one where you had like 2 threads.
Yep.
Could you also disable the optimization, like the optimizer, by making it volatile?
It's still not correct.
I know it's consensus.
I mean, the problem is if you have a multi-process machine, the thing is that L1 cache is local to each core, right? So if you happen to write to that gain on one core, and that cache stays hot all the time, and then another core tries to read from that value, it might see the old value for a very long time. I mean, the thing is, I think eventually it will be consistent. Like all platforms sort of have this eventually consistent, but you just have no idea of how long that might take. It's like completely unspecified until you finally see that new gain value on the other thread. I mean, mostly it will be, you're going to do a system call, a sleep somewhere, and a sleep, if it's doing a system call, is going to be an IO operation which synchronizes all of the memory anyway. So that's why in practice, it's normally not that much of a problem in this case, but you don't know. I mean, it's not very much defined, yeah.
I think by definition, volatile essentially says this is outside of the C++ memory model, which stops the optimizer doing the reordering. Does it?
No, you're right, but I think like volatile is very, like compilers implement it very differently.
Yeah, okay. So it might stop it doing the optimizations, but as Fabian said, it's not really going to help you with the synchronization of loads and stores. So use stood atomic. Just use stood atomic. Don't use volatile because it's being deprecated as part of the standard in lots of kind of scenarios anyway. So because no one implements it consistently. just avoid volatile at all costs.
Yeah, well, it was mostly for the first example where the gain you don't.
I mean, even with the cache, I mean, just real briefly, if your gain would depend, like if, let's say this would not be a gain but an index into some wave table, then you have a real problem because modern CPUs have pipelining and they do instruction reordering inside the hardware. So even if you don't have an optimizer, your CPU is a tiny little optimizer that will reorder instructions. And then, a load might happen before a store, but you wrote it the other way around. And the CPU is not allowed to do that if you use std atomics. So turning off the optimizer is not a solution. Right?
If you just need to share a value, like we said, and you use std atomic with relaxed memory ordering, instruction-wise, it will boil down to the same thing as using a float, but it will stop the optimizer messing around with your stuff. But really think about whether you can use a relaxed atomic or whether you just like, no, it's fine, I'll use sequential consistency, because that's most situations.
Okay, now we've definitely overrun 4 minutes.
Yeah, sorry, we've overrun. Everyone wants to, go grab a coffee or something. We'll be back here soon.